Hey everybody, it's Ripley back again. Today we're gonna what I did in a lot of textbooks, what they'll do is they'll bust the integral and comparison tests up into two sections. I don't really feel like we need to do that because there's really only one comparison or one of the tests in this that's even tricky, even a little bit, because everything else falls out from what we've already known about improper integrals, and things of that nature. It's called the limit comparison test, which we'll discuss here in just a minute. But what we're really getting into now is kind of the weeds of tests for convergence of series, right? So we've got an infinite series A sub n. Now let's review really quickly, because we know a little bit, we know some things about some series in terms of convergence or divergence. We know the divergence test, which I'll just call dt. We know that if the limit as n goes to infinity of a sub n does not equal 0, this automatically implies that the series a sub n diverges. Now remember though, if it does equal 0, it doesn't mean anything because we know that this diverges. That's the harmonic. Excuse me. Okay, so we got that one. We also know that the sum of a r to the n, as n goes from 0 to infinity. I get a little lazy with my notation on my sums. You can yell at me down the road for that. But remember, this guy is a plus ar plus ar squared plus ... for forever. This converges. This converges if absolute r is less than 1. This guy is commonly referred to as the geometric series. Okay, so we do know we've got some just some cornerstones that we can build everything else on. Now, let me show you a little something here. We're getting into the thick of it, and like I said before, and I know that you're like, well, Ripley, why is this so important? Way back when we talked about improper integrals, or excuse me, way back when we talked about sequences. Remember what a sequence was? Sequence was this is not whoops. That's supposed to be a set notation. Sorry, a sequence is just this guy, a sub n, right? It's just a box full of ordered things. Remember that we said that a sub n is equal to f of n. And I emphasize that over and over and over again. It gives us a nice kind of visual context to work in, but it's also going to get really helpful for a couple of the tests that I'm going to give you right now. Let's talk about the integral test. And I think the integral test, you're going to be like, all right, that makes sense, especially based on what we've already known about improper integrals and this relationship between sequences and functions. All right, so the integral test is real simple. Now, let's think about this. If I have a function, let's say, for example, 1 over x squared. So I've got f of x equals 1 over x squared, right? And we know that the integral from 1 to infinity of 1 over x squared dx converges. How do we know that? Why? Because I can either say because p is greater than 1 or p is equal to 2. Remember, it's that p integral. Well, think about this. If the integral converges, let's use an obnoxious color, then clearly, I know this is not correct, but bear with me for a sec. Then clearly, the sequence must also converge, because if I add up all the area under the integral, and that converges, then me cherry picking a few values that are determined by the natural numbers must also converge. Do you agree with that? Okay, that makes sense, doesn't it? All right, now that's just one example. What the integral test says is this. It says 1, if the integral from 1 to infinity of f of x dx converges, all right? Excuse me. Then this implies that the series a sub n from n equals 1 to infinity must also converge. Okay? Now, this is where a sub n equals f of n. In other words, we're cherry picking those values. Another way to think about it is this. Let's change colors one more time. We'll grab my blue. Think about this. If this is f of x equals 1 over x squared, which we know converges, do you agree that I could build rectangles that looked like this, right? Build rectangles that looked like this, etc., etc. Now, each one of these would be 1 wide, and they would be, this guy right here would be f of 1, clearly not drawn to scale, f of 2, f of 3, f of 4, right? Do you agree that the area of this rectangles, if I added all these up, they would have to be less than the area of the integral? Because, I mean, look at it. It lays under it. Now, you may say, well, what about this extra? Well, that's all going to get picked up. Now, likewise, we can make exactly the same argument of, let's say, if the integral from 1 to infinity of f of x dx diverges, then this implies that the sum, as n goes from 1 to infinity of a sub n, must diverge as well, where a sub n equals f of n. Now, this is going to seem really crazy, but let's just do 1 over x. We know that 1 over n. We know that 1 over n diverges, but let's suppose for a minute that we didn't. We certainly know, if this is f of x equals 1 over x, we know, we proved it back with improper integrals, with the p integrals, that the integral from 1 to infinity of 1 over x dx diverges. Now we can also say, watch this, this will make you a little crazy, but it's fun. If I go up here, and then here, and then here, and then here, and then here, what I can do is I can make rectangles that are actually bigger in comparison. I'm going to use that word quite a bit here in a little bit. That are actually bigger in comparison than this integral, right? Isn't that crazy? So if I've got values that are larger for as I move my way down, remember each one of this starts at 1, and this is 2, 3, 4, 5, 6. In other words, the area of the blue is greater than the area under the curve of the black, and we already showed that the area under the curve of the black diverges, right? That implies that the series must also diverge. So that's the integral test. Now, I will tell you, integral test is kind of the nuclear option of proving convergence or divergence. You don't really want to use it if you don't have to. However, a ramification of the integral test is fabulous. All right, one of the ramifications, because of the marriage between sequences and functions, and because of what we already know about improper integrals, remember the integral from 1 to infinity of 1 over x to the p dx. This converges if p is greater than 1, and it diverges else. Well, now we've got this marriage. Therefore, I now have what's called a p-series because of the marriage between a sub n and f of n. I can say as n goes from 1 to infinity of a sub n. Now I'm speaking all proper. This is going to, whoops, I don't want a sub n. I want 1 over n to the p, n to the p. This is going to converge if p is greater than 1. It's going to diverge else. This is called a p-series, just like we called it the p-integral before. Now, remember that this 1 to infinity, this n equals 1, or this starting at 1, was pretty arbitrarily chosen. I can start this thing at 17,000 if I want to, because if I add up a finite number of terms, as long as the terms are all defined, then I'm definitely going to converge. So we'd say just by convention that we'll start at n equals 1, but I can really start n wherever I want, as long as it's positive, of course. It's a positive whole number, or a natural number. Whole would be 0 as well, remember that. Okay, so there you go. You got your p-series, you've got your integration test. P-series is going to be one of your very, very, very best friends. Okay, so that takes care of the integral test. Now, I'm going to meet you back here in just a second. We'll talk about comparison test and limit comparison test. Believe it or not, this is a relatively short section. It's just 3 really powerful tests, and of course, p-series is. All right, I'll see you back in just a second. Okay, now we're going to talk about comparison tests. Now, I was pretty glib and didn't do any real examples with integral test, which we'll do a bunch of those in class. You know, like if I had the sum, which, I mean, the worst part about this is that this would need to be from 2, like I said, it's got to be defined, of like 1 over n ln n, right? Well, we showed before that the integral from 2 to infinity, this is the one that drives me crazy, of x ln x dx, that this guy diverged, right? So we would say, since, let's put a since in here, since this guy diverges, this implies that the sum as n goes from 2 to infinity of 1 over n ln n diverges by integral test. And we're done. It's that simple. The hard work with the integral test, and this is why we don't want to necessarily use it very often, the hard work is done doing the actual integral, which I didn't do because we've done it before. All right, let's talk about something called a comparison test. Ooh, wait, we've heard of comparison tests before. Ripley, what are you talking about? Hey, guess what? It's exactly the same comparison test because what I'm about to talk about, A sub n, comes from f of n, and b sub n comes from g of n. We get to say the following. If, excuse me, a sub n and b sub n are series with positive terms. That's important because if they're not positive, just like remember back when we talked about improper integrals in the comparison test, they had to be positive terms. Positive terms. And I'm sorry, I just got interrupted. I apologize that. And if the series b sub n converges and a sub n is less than or equal to b sub n. Now, typically we say for every n, but remember, it doesn't have to be true for every n. You can transgress this statement right here as long as you do so for a finite number of terms. All right, that should be for every n, not for every subscript n. That looks goofy. All right, so as long as it's a finite number of terms, we don't worry about it. Now, let's look at what I've said. I just said b sub n converges. A sub n is, or the series b sub n, converges, not the sequence b sub n. And the series a sub n is less than or equal to b sub n for every n. What does that imply? This implies that a sub n, since the series a sub n, must also converge by a comparison theorem. It works exactly the same way it worked back when we were talking about improper integrals. 2, now you can probably write the other one. If, oh, I don't know why I did that. Let's do that. If b sub n, the series b sub n, diverges and a sub n is greater than or equal to b sub n for every n, remember, this is the Ripley asterisk. It doesn't have to be true as long as it's not true for a finite number of terms, all right, after which it's always true. This implies that the series a sub n must also diverge by the comparison test. Okay, now let me show you something. Let's do one real quick, because this is everything that I want to see. Remember those 3 steps that we had back with comparison tests for integrals? I get the same thing. All right, so we are going to determine, let's go n equals 1 to infinity, if 1 over n squared plus 2n plus 1 converges or diverges. So the question is C or D, question mark. Well, here's what we do. Hopefully you're looking at this thing and you're like, oh, this is pretty easy. I know that 1 over n squared plus 2n plus 1 is less than or equal to 1 over n squared for every n. That's obvious. I don't have to justify that. I think we all know that. We also know, since the series 1 over n squared converges. Why? Tell me why. Because p equals 2 or p is greater than 1. Either one of those will work. This implies that the series n goes from 1 to infinity. You can be a little bit lazy in between. I'll let you do that. In other words, I don't want you to be lazy. I can be a little bit, I should put 1 to infinity here. I can be a little bit lazy, but I'm not going to ding you if you forget to put that on there. However, at the end, we have to go back to our original series and we have to quote what it does and why. So this becomes 1 over n squared plus 2n plus 1, and this thing converges. Why? By CD. Period. Okay? That's a comparison test in a nutshell. Now, very much like techniques of integration, you are going to want to put your head down and only have one technique that works all the time, and that just doesn't work. Like, for example, I'm going to do this guy. Let's say n equals 1 to infinity of 1 over n squared minus 2n minus 15,000. Okay? Now, look at this. It's like, oh, good Lord. Is this thing gonna, I guess I gotta be a little bit careful. No, I won't end up with I don't think I'll end up with zeros in the denominator, right? I don't think this thing is factorable. Let's assume that it isn't for simplicity's sake, which I don't think it is. Okay, now I'm kind of screwed, aren't I? It's like, oh no, I can't really use the comparison test because I can't say that 1 over n squared minus 2n minus 15,000 is less than or equal to 1 over n squared. Doesn't work that way, right? That's not true. So what am I going to do? Well, I'm going to use something called the limit comparison test. Limit comparison test. And this is a great test. It's one of my favorites. And at first blush, it's like, what is this? This is insane. Limit comparison test. Okay, so all limit comparison test says is this. Suppose that the series A sub n and the series B sub n have positive terms. Okay, if they don't have positive terms, I guess that would make this one hoopty crazy, wouldn't it? Because I'm going to get some negative terms. Let me change this up a little bit. Well, n squared minus 2n. Well, where we get into trouble, oh man, what are we going to do here? Let's go plus 1. Plus 1, do I get, except I get a 0, let's go 2, right? Something like that. That'll work, right? Okay, is that going to work? Yeah, because a half isn't, what do I end up with? A 2 negative. Those go away, I end up with 1 is greater than or equal to, yeah, 1, what did I say, 2, 1/4. So that doesn't work. All right, let me change this so we're not too confused. Let's go plus, this is going to be plus 1. What I'm saying is you can't say this for every n. All right? However, this is a cool part. I'll show you how this works. If the limit as n goes to infinity of a sub n over b sub n is equal to some constant which is not equal to 0. All right? So some constant not equal to 0. This implies that either a sub n and b sub n, the series, both converge or both diverge. Now this seems kind of miraculous, and this can be really, really confusing, for students. They're like, wait, what? But if you think about it, look at what happens. What it's saying is if out at infinity, I've got two series that behave the same way, and I know one of the series converges. Then, if they behave the same way out at infinity, they're sort of undifferentiable from one another, right? They're the same series way out at infinity, and therefore they must either both converge or both diverge. Now, in this case, I've got this guy. I'm going to do the series as n goes from 2 to infinity of 1 over n squared minus 2n plus 1, which I know I could start it at 1 and then scrape off the transgressor, etc., etc. Now, but I'm not going to do that. I'll be good, I promise. Now, what I want you to notice is when we use limit comparison test is usually when we have god-awful, like rational function style series or square roots or things of that nature. So hopefully you notice that out at infinity, this guy right here behaves like 1 over n squared. And what do we know of it? These are all notes, by the way. I'm just doing dirt work. I'm putting these in parentheses. We know that 1 over n squared does what? Well, it converges. Why does it converge? Because p equals 2. Again, dirt work. All right? So the trick with this is always to select the correct a sub n. So, for example, what I'm going to do is I'm going to take the limit as n goes to infinity, and I'm going to use 1 over n squared over 1 over n squared minus 2n plus 1. I always put this mother sequence on top because it makes the algebra easier later. Okay? Now, what does this equal? This equals the limit as n goes to infinity of what? N squared minus 2n plus 1 over n squared. Hey, look at this. This is a rational function, right? It's just rational sequences which come from functions. The degree of the top is 2. The degree of the bottom is 2. When that happens out at infinity, not 0, I think that was supposed to be an infinity, take the ratio of the lead coefficients. Well, look at that. 1. Hey, guess what? That's not equal to 0. Now, we've got some work to do. All right, we just showed that this series, 1 over n squared, and this series, 1 over n squared minus 2n plus 1, behave the same way. What do we know about 1 over n squared, or the series 1 over n squared? We know it converges. Y, p equals 2, blah, blah, blah. But now we have to summarize all that. Since the series 1 over n squared converges, in parentheses, p equals 2, this implies that the series 1 over n squared minus 2n plus 1 also converges by LCT. Ta-da! Now, the bell's going to ring. I got to teach some kids. So I will meet you back here. I'll do one more example that's not quite as clear-cut in terms of why you use limit comparison test and how you use, hey, there's the bell, how you use comparison or limit comparison test. So I'll see you back here in a minute and we'll get that thing done. Have a good day, or not have a good day yet. I'll see you in a second. Okay, so there's one more example that I want to give to you guys, and it's pretty instructive. So we know that we're going to use the limit comparison test okay, like techniques of integration, there is no one-size-fits-all technique. So you have to be flexible in terms of what you're going to use. However, typically, if you have a rational sequence, and what I mean by that is you have a situation where you've got a sub n over b sub n, where these guys come from polynomial functions. So poly f of x's or f of n's. That's typically where you're going to use the limit comparison test. However, there's another one. What if I had the sum as n goes from 1 to infinity of the square root of, let's go n squared plus n plus 1 over n to the 4th plus 3. Okay, now, when you see one of these, your first reaction is going to be, "Whoa, what the heck is going on here?" However, don't panic. It still has this rational component to it. Okay, but when you have these square roots, if you have cube roots, but you've still got the rational sequences inside, just take a deep breath and look at what happens as n goes to infinity. All right, do you agree that at infinity, these chunks no longer matter? Hopefully you do, but you can't answer. So what really happens is you end up with this. This turns into, let's see, the square root of n squared is just n. The square root of n to the 4th is n squared. So this turns into 1 over n. Aha! And now we're happy. But the hard part about this is, okay, I'm guessing that this turns into 1 over n. We know this is all parenthetical, by the way. This is not considered work. This is dirt work on the side. We know the harmonic diverges. So chances are this guy's going to diverge. So the trick here is, here's what I do, is the very first step when I go to look for that a sub n, instead of using this guy, which, watch, when I go like this, so remember over here, when I use, let's see, where was it? I put my 1 over n squared on top because it made my algebra easier. If I do the limit, I don't know where that sum came from, if I do the limit as n goes to infinity, the limit as n goes to infinity of 1 over n over the square root of n squared plus n plus 1 over n to the 4th plus, was that a 3? Let's call it a 3, what the heck. All right, algebraically that looks really awful. So I don't want to take this approach. The approach that I do want to take, however, and I'll change colors to make sure you see it, is actually use this guy. So I'm going to take the limit. You'll see why in just a sec. You may be like, Ripley, but that looks the most complicated of all of these. Yeah, but it's got a square root and so does this. So algebraically speaking, we are going to want to deal with those square roots. So I've got this guy over, I've got n squared plus n plus 1 over n to the 4th plus 3. Now, if you recall, that's an n to the 4th. If you recall, I can actually throw this whole thing, I'll just change it to green. I can slap a square root over the whole thing and kind of ignore these guys. And then this turns into the limit as n goes to infinity. That's algebra, by the way. There's no calculus. There's no pre-calculus. This thing just turns into, when I multiply the top n squared by the bottom, right, the extremes by the means, I end up with n to the 6th plus 3n squared over, what do I end up with? N to the 6th plus n to the 5th plus n to the 4th square root over, let's see, what do I have here? Yeah, that's exactly what I want. So now I know that if I really wanted to be exhaustive, I could rewrite this, remember, because the compositions of continuous functions with limits and all that good stuff. But you don't have to do this. At this point, you should see that the degree of the top and the degree of the bottom are the same. It's going to be the ratio of the leading coefficients. However, if you really want to be kind of anal about it, you end up with n to the 6th plus n to the 5th plus n to the 4th plus n to the 4th. Is that what I want? That's what I want, isn't it? And it's extreme. Yeah, perfect. And this becomes the square root of 1, which is 1, which is a constant not equal to 0. All right, so the hard part here, excuse me, is that we now have to summarize everything. We already knew this thing was going to diverge because we knew out at infinity it behaved like this. All right. However, by now you should know, we write since, all right, the sum of 1 over n, if I want to be exhaustive, diverges. Why does it diverge? Because p equals 1, harmonic, whatever you want to write. This implies that the sum as n goes from 1 to infinity of the square root of n squared plus n plus 1 over n to the 4th plus 3 also diverges by LCT. Now, the hard part about LCT for me is that I am going to want to see, this work. You don't have to go into this move. All right, I want to see your rationalization, then I want to see you do the since, implies, diverge by LCT. LCT is a great tool. It's wonderful. However, it's got a lot of work to it, so you gotta be careful with that. Okay, I hope this was helpful. This is the last little chunk of the comparison tests and the ratio tests, and I'll shut up and let you guys get to it. Have a good day. We'll see you in class.